Welcome to Math Zone African Motives. In this tutorial, we will be diving into Module 4, focusing on trigonometric graphs. We will learn how to sketch the graphs of all 6 trigonometric functions. In this unit, our objective is to learn the process for sketching these graphs. Let's first understand the axes we'll be using. The horizontal axis, or x-axis, will always represent the angle in either degrees or radians. The vertical axis, or y-axis, will represent the ratio, which is the output or value of the trigonometric function for that given angle. Now let's look at the standard form for trigonometric graphs. Understanding this form is key to sketching and analyzing these functions. Trigonometric graphs are represented in their standard form as y equals a sine of the quantity bx plus c plus d. This same form applies to other functions like cosine and tangent, just by replacing sine with cosine or tangent. So, for cosine, it's y equals a cosine of the quantity bx plus c plus d, and for tangent, it's y equals a tangent of the quantity bx plus c plus d. Each of the parameters a, b, c, and d changes the standard graph in a specific way. Let's break them down. The parameter a is called the amplitude. It tells us about the peak or greatest value of the graph. It's the distance between the horizontal axis and the top of a wave. The parameter b is the frequency. This determines the number of complete cycles or waves we see within a specified interval. The parameter c is the phase shift. This is a horizontal displacement. It tells us how far the graph is shifted to the left or right from its starting position. Finally, d is the vertical shift. As the name suggests, this displaces the graph vertically, either up or down. Before we look at specific graphs, let's establish some important terminology. These terms are fundamental to describing and understanding periodic functions. First, a periodic function. This is an oscillating function, meaning it moves back and forth or up and down, where a pattern of y values repeats itself at regular intervals. Think of it like the tides of the ocean, which repeat a pattern every day. Next, let's define a cycle. A cycle is one complete repetition of that repeating pattern of y values. Imagine taking a snapshot of one full wave. That snapshot would be one cycle. The length of a cycle is called the period. The period is the horizontal length of one cycle. If we say a graph has a period of 360 degrees, it means one full wave repeats every 360 degrees along the x-axis. We will see how these concepts apply as we look at the specific sine, cosine, and tangent graphs. Let's begin with the sine graph, the foundation for many of our explorations. Our objective here is to understand the standard sine graph, the equation y equals sin of x. First, a quick note on the units on the x-axis. While we often use degrees, they can also be represented by their radian equivalents. Remember, 360 degrees is equivalent to 2 pi radians. Therefore, 180 degrees is pi radians, 90 degrees is pi over 2 radians, and 270 degrees is 3 pi over 2 radians. We'll use degrees for this section. Let's draw the standard sine graph on a domain from 0 to 360 degrees. Here is the equation we are graphing, y equals sine of x. We start with our coordinate system. The x-axis represents the angle in degrees from 0 to 360, with major tick marks at 90, 180, and 270. The y-axis represents the sine ratio, ranging from 1 to 1. Now, let's plot the key points of one cycle. At 0 degrees, the sine of 0 is 0, so we have a point at the origin. At 90 degrees, the sine of 90 is 1, our maximum value. At 180 degrees, the sine of 180 is 0. At 270 degrees, the sine of 270 is 1, our minimum value. And at 360 degrees, the sine of 360 is again 0, completing the cycle. Connecting these points with a smooth, oscillating curve gives us the standard sine graph, equals sine x. This curve represents one full cycle of the sine function. So we have successfully sketched the standard sine graph. It's a continuous wave that oscillates between a maximum of 1 and a minimum of 1. Now that we understand the standard sine graph, y equals sine x, let's investigate how the parameter a, the amplitude, influences it. We will look at the graph of y equals 2 sine x. Here the parameter a is 2. What does this a value of 2 do to our standard sine wave? The text tells us the amplitude is doubled. Amplitude is the distance from the horizontal axis to the crest or trough. For y equals sine x, the amplitude is 1. If we double the amplitude, the new amplitude should be 2. Let's confirm this by drawing the graph. We'll use the domain from 0 to 360 degrees. First, we draw our axis and the standard sine graph as a dashed line for comparison. Now for our new function y equals 2 sine. We take the key points of the standard graph and multiply their y values by 2. At 90 degrees, y was 1, now it's 2. At 270 degrees, y was 1, now it's 2. The x-intercepts at 0, 180, and 360 degrees remain the same because anything times 0 is 0. Connecting these new points, we get a wave that is twice as tall as the standard one, oscillating between 2 and 2. This confirms that the amplitude has indeed been doubled. So we've seen how the parameter a scales the graph vertically. A larger a makes the wave taller, and a smaller a, like a fraction, would make it shorter. The amplitude for y equals 2 sine x is 2. Statistics. Next, let's explore the effect of the parameter b, which is related to the frequency of the graph. We will now look at y equals sine 2x. In our standard form, y equals a sine of bx plus c plus d. The parameter b is 2. The document states that the frequency b is doubled. What does this mean? It means we should see twice as many cycles in our domain of 0 to 360 degrees. The frequency b tells us how many complete cycles occur in the standard period of 360 degrees. Since b is 2, we should find 2 cycles in this range. Alternatively, we can calculate the new period. The formula for the period of a sine or cosine graph is 360 degrees divided by the absolute value of b. Using the formula, the period is 360 degrees divided by 2, which gives us 180 degrees. This means one complete cycle of the graph now happens in only 180 degrees. This confirms the frequency is doubled and the period is halved. Let's draw our axes with the standard sine graph as a dashed line for reference. Now the key points of y equals sine 2x occur twice as fast. A cycle completes at 180 degrees, not 360. This creates a second identical cycle from 180 to 360 degrees. We can see clearly that the solid line, y equals sine 2x, completes 2 full waves in the same space that the dashed line completes 1. The frequency has been doubled. To recap, the b parameter scales the graph horizontally. A b greater than 1 compresses the graph, increasing the frequency and shortening the period. A b between 0 and 1 would stretch the graph, decreasing the frequency and lengthening the period. We will now see how the parameter c affects the graph. The text refers to this as a horizontal displacement or phase shift. Let's first look at y equals sine of the quantity x plus 30 degrees. The phase shift c is 30. The description says there is a horizontal displacement of 30 degrees to the left. Take a moment to think about why a plus sign inside the parentheses results in a shift to the left. This might seem counterintuitive. Why does adding 30 degrees shift the graph left in the negative x direction? Let's consider a key point. The standard sine graph has a maximum at x equals 90 degrees. For our new graph, y equals sine of x plus 30 degrees. The maximum occurs when x plus 30 degrees equals 90 degrees. Solving for x, we get x equals 60 degrees. So the maximum has moved from 90 degrees to 60 degrees, which is a shift of 30 degrees to the left. As always, we start with the standard sine graph as our guide. Now we'll draw a new graph by taking every point on the dashed line and shifting it 30 degrees to the left. The x-intercept that was at 0 degrees is now at 30 degrees. The maximum that was at 90 degrees is now at 60 degrees. Every point is displaced 30 degrees left. Now let's examine the opposite case. For y equals sine of the quantity x minus 30 degrees, the phase shift c is now negative 30. The document states this is a horizontal displacement of 30 degrees to the right. Let's apply the same logic. The maximum of the standard sine wave is at 90 degrees. For our new graph, the maximum is when x minus 30 degrees equals 90 degrees. This gives us x equals 120 degrees. So the maximum has shifted 30 degrees to the right. Again, we draw our axes and the reference graph. This time, we shift every point of the standard sine wave 30 degrees to the right to get the graph of y equals sine of x minus 30 degrees. So, to summarize, the parameter c shifts the graph horizontally. If you see plus c inside the parentheses, the shift is c units to the left. If you see minus c, the shift is c units to the right. It's the opposite of what your intuition might suggest. We've looked at amplitude, frequency, and phase shift. Now let's investigate the final parameter, d, the vertical shift. First, let's graph e equals sine of x minus 1. Here, the vertical shift parameter d is negative 1. The document tells us the graph is displaced vertically downwards by 1 unit. This is much more intuitive than the phase shift. A minus 1 outside the sine function means we simply subtract 1 from every y value. Let's use our reference graph. The standard sine wave oscillates between 1 and 1, centered on the x-axis, or y equals c0. If we subtract 1 from every point, the entire graph will move down. The new center will be the line y equals 1. Here is our setup with the dashed standard sine graph. For y equals sine x minus 1, we subtract 1 from each y coordinate. The points 0, 0, 90, 1, 180,000, 270,000, 360,000 become 0 to 1, 90,000, 180,000, 270,000, and 360,000. We can see the new graph oscillates between 0 and 2, with its center at y equals 1. It has shifted down by 1 unit. Next, let's consider y equals sine of x plus 1. Here, the vertical shift d is positive, 1. As expected, the document says the graph is displaced vertically upwards by 1 unit. A plus 1 outside the function adds 1 to every y value. So, our new graph will be centered around the line y equals 1. Its oscillation will be between 0 and 2. Using our standard sine graph as a guide, we now shift every point upwards by 1 unit. The point, so 0 moves to 0 to 1. The point 90.1 moves to 90.2. The entire graph moves up with the new midline at y equals 1. In summary, the parameter d moves the entire graph up or down. A positive d shifts it up, and a negative d shifts it down. This shift affects the maximum and minimum values of the function. Now let's apply everything we've learned with a comprehensive example. Example 416 asks us to draw 4 graphs on the same system of axes for a domain between negative pi and pi. Remember, pi radians is 180 degrees. The 4 equations are y equals sine a x, y equals 1/2 sine a x, y equals sine of x minus 45 degrees, and y equals sine x minus 1/2. First, we draw our axes. The domain from negative pi to pi means from negative 180 degrees to 180 degrees. We start with the first equation, y equals sine x. This is our standard sine graph. Let's draw it in red. Next, the second equation is y equals 1/2 sine x. This is an amplitude change where the amplitude is 1/2 as tall as the red curve. To graph this, we take the red graph and multiply every vertical value by 1/2. The maximum at 90 degrees goes from 1 to 1/2. The minimum at negative 90 degrees goes from negative 1 to negative 1/2. This gives us a shorter wave. Let's draw it in blue. The third equation is y equals sine of x minus 45 degrees. This is a phase shift. The minus 45 degrees tells us to shift the graph 45 degrees to the right. We can shift the key points of the standard red graph 45 degrees to the right. For example, the x-intercept at 0 moves to 45 degrees. The maximum at 90 degrees moves to 135 degrees. The minimum at negative 90 degrees moves to negative 45 degrees. Let's draw this shifted wave in green. Finally, the fourth equation is y equals sine x minus 1/2. This is a vertical shift, where we move the entire graph down by 1/2 unit. We take the red standard graph and subtract 1/2 from every vertical value. The x-intercept at 0 moves to negative 1/2. The maximum at 90 degrees moves from 1 to 1/2. The minimum at negative 90 degrees moves from negative 1 to negative 1.5. This gives us a graph shifted down. Let's draw it in purple. And there you have it, at all four graphs on the same axis. We can clearly see the effect of each parameter. The red line is the standard graph. The blue line has a smaller amplitude. The green line is shifted right, and the purple line is shifted down. Let's move on to Activity 4.5. The first question asks us to state the amplitude, minimum value, and maximum value for each graph from Table 4.1. Remember, the amplitude is the absolute value of A. The maximum value is d plus amplitude, and the minimum value is d minus amplitude. Let's apply this. For y equals sine x, A is 1 and d is 0. So the amplitude is 1. The maximum is 0 plus 1, which is 1. The minimum is 0 minus 1, which is negative at 1. For y equals 2 sin x, A is 2 and d is 0. The amplitude is 2. The maximum is 0 plus 2, which is 2. The minimum is 0 minus 2, which is negative 2. For y equals sine of 2x, A is 1 and d is 0. The amplitude is 1. The maximum is 0 plus 1, which is 1. The minimum is 0 minus 1, which is negative 1. For y equals sin of x plus 30 degrees, A is 1 and d is 0. The amplitude is 1. The maximum is 1 and the minimum is 1. For y equals sine of x minus 30 degrees, A is 1 and d is 0. The amplitude is 1. The maximum is 1 and the minimum is 1. For y equals sine x minus 1, A is 1 and d is 1. The amplitude is 1. The maximum is 1 plus 1, which is 0. The minimum is 1 minus 1, which is negative 2. Finally, for y equals sine x plus 1, A is 1 and d is 1. The amplitude is 1. The maximum is 1 plus 1, which is 2. The minimum is 1 minus 1, which is 0. We have now stated the amplitude, min, and max for all 7 graphs. Let's move on to the second part of Activity 4.5. Here, we need to sketch 3 graphs on the same system of axes for the domain from /180 to 180 degrees. The 3 equations are y equals sine x, y equals sine of 3x, and y equals 3 sine x. First, we set up our axes. The domain is from negative 180 to positive 180 degrees, and the y-axis should accommodate an amplitude of 3, so let's go from 4 to 4. Equation 2.1 is y equals sine x, our standard graph. We'll draw one cycle from up 180 to 180. It starts at 0, goes down to 1 at 190, up to 1 at 90, and back to 0 at 180. Let's make this our solid red reference line. Next, equation 2.2 is y equals sine of 3. This involves the frequency parameter b, which is 3. The period will be 360 divided by 3, which is 120 degrees. A period of 120 degrees means one full cycle completes in 120 degrees. From a 180 to 180, we have a total range of 360 degrees. So we will see 3 full cycles. Let's draw this in blue. Finally, equation 2.3 is y equals 3 sine x. This involves the amplitude parameter a, which is 3. The amplitude is tripled. To graph this, we stretch our standard red graph vertically by a factor of 3. The maximum will be 3, and the minimum will be 3. Let's draw this in green. This gives us a much taller wave. Here are all 3 graphs on the same system of axes. We can clearly see the effects of amplitude and frequency. We're almost done with the activity. Let's tackle the third part, where we again need to sketch graphs on the same system of axes for the domain from 180 to 180 degrees. This time, the equations are y equals sine of x plus 45 degrees and y equals sine x plus 0.5. We set up our axes. The domain is from 180 to 180. The y range can be kept from 2 to 2 to clearly show the shifts. Again, let's include our standard graph, y equals sine x, as a dashed reference line. We'll draw it in red. Equation 3.1 is y equals sine of x plus 45 degrees. This is a phase shift. The plus 45 degrees inside the parentheses means we shift the graph 45 degrees to the left. Let's shift the key points of our dashed red line. The x-intercept at 0 moves to 45. The maximum at 90 moves to 45. The x-intercept at 180 moves to 135. Let's draw this shifted graph as a solid blue line. Equation 3.2 is y equals sine of x plus 0.5. This is a vertical shift. The plus 0.5 outside the function means we shift the graph 0.5 units upwards. Now we take our dashed red line and add 0.5 to every y value. The x-intercept at 0 becomes 0, 0, 0.5. The maximum at 90 moves from 1 to 1.5. The minimum at 90 moves from 1 to 0.5. Let's draw this in green. And here we have the three graphs on the same axis. The dashed red line is the standard sine graph. The solid blue line is shifted left by 45 degrees, and the solid green line is shifted up by 0.5 units. This completes part 3 of activity 4.5. Now let's turn our attention to the tangent graph. The objective of this section is to understand the equation y equals tangent of x and its unique features. To understand why this graph looks different, recall the definition of tangent. Tangent of x is defined as the sine of x divided by the cosine of x. Since division by 0 is undefined, the tangent function is undefined whenever cosine of x is 0. Cosine is 0 at negative 90 degrees, positive 90 degrees, and so on. These are the locations of the graph's asymptotes. An asymptote is a line that the graph approaches but never actually touches. The tangent graph has vertical asymptotes at x equals negative 90 degrees and x equals 90 degrees within our domain. Let's draw our axes. We mark the asymptotes as vertical dotted lines at 90 degrees and 90 degrees. We also mark key points. Tangent of 180 is 0. Tangent of 0 is 0. Tangent of 180 is 0. These are the x-intercepts. Now we sketch the curves. Each branch of the tangent graph originates from negative infinity, passes through an x-intercept, and goes towards positive infinity, approaching the asymptotes. Let's talk about the parameters a, b, c, and d for the tangent graph. The document states that they affect the tangent graph in the same way they affect the sine graph. So EA changes the steepness of the curve. A larger A means a steeper curve. B changes the frequency and period. The period of tangent is 180 degrees, so the new period would be 180 divided by B. C is the horizontal shift, and D is the vertical shift. We will explore some of these effects in a later example. Finally, we will look at the graphs of the reciprocal trigonometric functions, secant, cosecant, and cotangent. We will examine the graphs of y equals secant x, y equals cosecant x, and y equals cotangent x within the domain from lot 180 to 180 degrees. An important exam tip is provided here. You do not need to work with the effects of parameters a, b, c, and d on these three reciprocal graphs for your exams. This simplifies things greatly. We only need to know the basic shapes. The easiest way to graph these is to first graph their reciprocal function. For y equals secant x, we first graph y equals cosine x. The graph of secant x has vertical asymptotes wherever cosine x is 0, which is at negative 90 and positive 90 degrees. At other points, secant x will be the reciprocal of cosine x. The graph forms U-shaped parabolas opening away from the x-axis. Next, let's look at y equals cosecant x. We graph its reciprocal y equals sine x. Cosecant x has asymptotes wherever sine x is 0, at negative 180, 0, and positive 180 degrees. The graph forms U-shaped parabolas opening away from the x-axis, alternating between positive and negative values. Finally, we have y equals cotangent x. We graph its reciprocal, y equals tangent x. The asymptotes for cotangent x occur wherever tangent x is 0, which is at negative 180, 0, and 180 degrees. The cotangent graph also passes through 0 at the locations of tangent's asymptotes, which are notch 90 and 90. Its branches descend from left to right between the asymptotes. By following this method of first graphing the reciprocal function, you can easily reproduce the basic shapes of the secant, cosecant, and cotangent graphs. That brings us to the end of our tutorial on trigonometric graphs. We've covered a lot of ground today. We started by understanding the general form of a trigonometric graph. Y equals a sine, cosine, or tangent of bx plus c plus d. We learned that A controls the amplitude or steepness, B controls the frequency and period, C is the horizontal phase shift, and D is the vertical shift. We explored each of these parameters in detail using sine graphs, and we saw how they transform the basic wave. We then moved on to the tangent graph, understanding its unique characteristic of vertical asymptotes and how to sketch its branches. Finally, we tackled the reciprocal graphs, secant, cosecant, and cotangent, learning that the easiest way to sketch them is by first graphing their reciprocal functions and using them to find the asymptotes and key points. By following these step-by-step methods and understanding the parameters, you are now well equipped to sketch and analyze a wide variety of trigonometric graphs. Thank you for joining me. Subscribe for more tutorials from Math Zone African Motives. See you next time.